Well, we hope it'll just, you know, go down. Levels will go down. This is what we're told. They'll go down, but they told us it would be only on for 70 days, and of course, here we are, November, and it's still on.
Because if you can't see this radio cesium, and you can't find it without machines, how on earth are we going to get rid of it? What's going to happen to my farm? I believe it's been blighted, if that is the case. And even if it's going to take 20 or 25 years, it's going to have a big devaluing effect. These are some of the questions I would like answered.
Those are two Cumbrian farmers filmed back in 1986, about 6 months after the Chernobyl nuclear disaster. And both of them had had restrictions placed on the sale of their sheep because of the radioactive fallout that reached Cumbria from Chernobyl. Their comments reflect the widespread concern and uncertainty felt at the time about how long those restrictions would last. The problems were due to ions of two radioactive isotopes, cesium-134 and cesium-137. And these were incorporated into the vegetation and then concentrated in the sheep that grazed on it. The early predictions were that the vegetation and the sheep would be free from contamination in a matter of months. But even now, in the autumn of 1990, and more than 4 years after Chernobyl, there are still areas in the Cumbrian uplands here which are still too contaminated to allow the sheep that graze there to be sold for meat. So the question is, why were those early predictions so wrong?
Well, the predictions were based very largely on lowland systems, where the soil characteristics are different to the upland systems, which is where we actually have the problems. But first of all, I should just say that we know we're looking at Chernobyl cesium here because it's got a characteristic mix of cesium-134 and 137, and it's quite different to any other sources of cesium in the environment. Anyway, the lowland soils have got a much higher clay content, a much lower organic and content and lower acidity. And the clay content's very important because the clay minerals will bind the cesium and make them unavailable for plant roots. But if we look at an upland soil, it's got a much higher organic content, much higher acidity, and much less clay present. And not only that, but the clays that are present are not so effective because of the organic content and the acidity. So the cesium remains much more available for plant root uptake.
So not fully recognising the properties of upland soils is one reason why the predictions were wrong. But over and above that, the problems facing the Cumbrian farmers are compounded by another factor. And that's the way in which the plants on which their sheep graze absorb and then hold on to nutrient ions taken from the poor upland soils. One of the main aims of this programme is to look at ion uptake in plants, which, as it happens, takes us to the starting point of the Chernobyl cesium story. The accident itself occurred on Saturday, the 26th of April, 1986. A plume of radioactive material was ejected into the atmosphere, which in the week that followed drifted across Europe. By the following Saturday, Britain came under its shadow. The plume spread and divided in the prevailing winds, and being a bank holiday weekend, it coincided with rain across most of the country, much of it heavy. This carried a great deal of the radioactive material, including isotopes of cesium, down to the wet British landscape beneath. Once in the soil, the cesium was available to plant roots, where it was absorbed along with the normal soil nutrients. But before we look at what happens to the cesium, let's consider what the normal nutrients are and what plants do with them, at least in the lowlands. And one approach to that is through a controlled experiment. These tomato plants were grown in clean sand and then watered with a medium that contained either all the major nutrients, and that's this plant, the control, and a fine, healthy plant it is, or that contained none of them. And this poor, miserable plant shows what happens if none of the major nutrients are supplied. But if you look what happens if one at a time the major nutrients are withheld, you begin to see that there are specific deficiency symptoms. Now, this nitrogen deficient plant, well, it's almost as sick as this one. It's very spindly, it's thin and pale, and it's hardly surprising because nitrogen is a component of most of the major macromolecules in plants, the proteins, the nucleic acids, and lots of other compounds too. So plants can't grow without it. You compare that with the phosphate deficient plant. Now, this isn't as small, the growth is not as inhibited, but you do get a rather dark green colour on the leaves, and they tend to be clawed. And down here, the leaves show this very marked purple coloration. Phosphate, like nitrogen, is a component of many of the important macromolecules, the phospholipids, nucleic acids, and so on. But now, if we go to potassium deficiency, here the lower leaves are very yellow, many of them dying and falling off, and you get this, again, dark green colour at the leaf tips. Now, potassium, which is the ion that is closest to the cesium ion, is not present in macromolecules in plants. In fact, it's there largely as the free ion in the cell vacuoles, where it contributes to osmotic pressure. Magnesium deficiency. Here, one of the most characteristic things is this yellowing between the veins of the leaf. Now, that's because magnesium is a component of chlorophyll, the light-absorbing green pigment, and overall growth is strongly inhibited, of course. And finally, calcium deficiency. Now, this plant shows the smallest effect of all, and that's largely because it is very difficult to get media and sand that are truly free of calcium, and the plants don't need an awful lot of calcium. But where you do begin to see deficiency symptoms is not, as in all these plants, in the lower leaves, but at the stem tip and in the young leaves. You get this characteristic dieback and necrosis. Now, tomato plants have a high demand for mineral nutrients. You supply them, and they grow. Withhold them, and they don't. In other words, growth rate and nutrient supply are very closely matched. But that doesn't apply to all plants. You take a plant like this little common heath, Erica cinerea, which occurs on the uplands. Now, this plant can grow with very low supplies of nutrients. In fact, it probably wouldn't show deficiency symptoms with any of the media that we've used here. But equally, it would never attain the size and the growth rate of this controlled tomato plant. So obviously, plants vary both in their response to mineral nutrients and in the extent to which they can extract them from a nutrient-deficient soil. And to find out more about that, we've got to look at the soil and also at the organs that actually absorb mineral nutrients from it, at the roots. To maintain nutrient supplies to the plant, roots must grow continuously to exploit new soil, and roots are very well adapted to extracting nutrient ions from the soil around them. Just look at the development of root hairs, for example, in this nutrient-rich zone. Increased growth of root hairs and root branching when nutrients are plentiful is one mechanism that allows plants to maximize ion uptake. And for most plants, especially in poor soils, nutrient uptake can be boosted still further by another mechanism. To find out more, I visited the Merlewood Research Station in Cumbria on a fittingly wet day. There I spoke to Jill Clint about one of my particular interests,
fungi which form symbiotic associations with roots and increase their nutrient uptake. Such associations are called mycorrhizas.
At Millwood, we're very interested in the ecological significance of mycorrhizas, including the role they play in the transfer of caesium in upland pastures. As you know, most of the fungal network is invisible because it's below the soil surface, but evidence of the existence of mycorrhizas can often be seen in woodland areas when they form fruiting bodies or toadstools which are above the soil surface. And here we have some.
Oh, lovely array. Oh, yes. And, yeah, it's a cortinarius, isn't it? The rusty spores underneath. Now that, presumably, then, is getting all its sugars from the host plant, the tree here, which is its symbiotic partner,
yes,
and supplying mineral nutrients back to the tree.
That's right, so the system is beneficial for both.
It certainly is, yeah.
Come into the lab and I'll show you some more.
Oh, thank you. Oh. Just going to bring it this way, too.
I've got some pine plants here to look at. This one here is pine seedlings with a mycorrhizal infection in the roots, and this is the non-mycorrhizal control. And I think you can see there are very large differences in the size of the two sets of plants.
I certainly can.
Despite the fact that they're all the same age.
That's very impressive. So this mycorrhizal plant really has a good deal here.
That's right. Even in mature mycorrhizal trees, which are giving up to 25% of their sugars to the fungus, they still tend to do better than the non-mycorrhizal controls because they're receiving mineral nutrients in return. We can actually see the developing mycorrhizas on this specimen here in a tube. The long dark brown structure is the plant root, and around the outside of it, the lighter coloured material is the fungal material forming a mycorrhiza.
It's impressive the way the fungi extend so far away from the root there.
That's right. And in well-developed mycorrhizas, in these more mature specimens, you can actually see the mycorrhizal roots, and you can see that these are much thicker than the non-mycorrhizal ones.
Much thicker, yes. It's a very striking difference there.
And that's because of the presence of a sheath of fungal material around the surface of the root, which we can see in more detail under the microscope if you'd like to have a look.
Oh, right.
Now, because the fungal material is around the outside of the root, we call this form of mycorrhizal infection ectomycorrhizal.
Right, and that's the dark brown sort of layer all around the outside of the root. That's fungal hyphae.
That's it, yes,
that's
on
the
the
ecto
outside.
part of the mycorrhiza.
That's correct,
I see,
yes.
Right. It's very obvious, and that's the kind that you get in trees like the pine.
In woodland areas, yes.
Right, but is that important in the Chernobyl story?
No, not in the bit that we're interested in. We're interested in mycorrhizas that form associations with upland pasture plants, and these are of a quite different form. You can't see them with the naked eye, and in this case we've got a slide of an upland grass, sheep's fescue, which has been stained so that the fungal material is pink.
Oh, so the pink threads, that's the fungal hyphae?
That's right, yes.
They really do penetrate right into the cells. And that's obviously the endo bit of this mycorrhiza.
Yes, because they actually penetrate the root cells, it's called endomycorrhizal.
That's beautiful.
That's right. Now, these endomycorrhizas don't form the same exotic fruiting bodies as the ectomycorrhizas. If you'd like to pass me those plants. But physiologically speaking, the deal is just the same. These are plants of a common upland species, Trifolium repens, the white clover. And this is the mycorrhizal plant, and this is the non-mycorrhizal control. And I think you can see there are big differences in the health and the size of the plants. The mycorrhizal ones are doing much better.
Well, it appears that the endomycorrhizal nature of essentially all the upland plants is an important element in the Chernobyl cesium story, at least so far as the sheep farmers are concerned. But before we go into that, it's worth pausing to look in more detail at the structure of a root and how it functions in iron uptake. And this is a model of a root tip, the part that is pushing through the soil. The surface you see here isn't root surface cells. It's actually the sheath of mucus and bacteria and debris that coats the surface of the root, the rhizosphere it's called. You can see the root cells if you look down on the cross-section. These projections out here are the root hairs, and they're extensions from just single
epidermal cells, the epidermis, this outer layer of cells here. Now, ions and water can go into the root hairs or into the epidermis, and then they can cross the cortex, diffusing down an electrochemical gradient, inside the continuum of living cells, the symplast. Or, instead of that, they can move not inside the cells, but outside, along the cell wall or apoplast route, and that's the way that calcium goes. But the apoplast route is blocked once you get to this layer here, the endodermis, because its walls have a layer of thickening, the Casparian strip, which is waterproof. So it blocks the apoplast pathway. So entry into the stele, this central part, has to be via the symplast of the endodermis. And once into the stele, the ions can diffuse across to the xylem and from there be transported up to the shoot. You can see the xylem better if we look at a longitudinal section. The xylem cells now down the middle, they're very young ones, and you can see this spiral lignified thickening in their walls. And then at the tip of the root, here's the root cap. Now this protects the root tip as it pushes its way through the soil. It's very tough going out there. I mean, it's rough. And this root cap gets worn away, and then it's replaced by cell divisions in the meristematic zone here. And then ions and water are taken in all over this root tip zone down here. Although, of course, they can only get up to the shoot if there's xylem present. But as the ions are taken in, they tend to deplete the soil immediately surrounding the root in a zone surrounding the epidermis. And for a particular ion, the width of this depletion zone, as it's called, will vary, depending on the mobility of the ions. For something that's very immobile, like phosphate, and phosphate tends to be in very short supply in the upland soils, it's an extremely narrow zone, millimetre or less. And in effect, the root's exploiting only a tiny volume of soil for phosphate. This is where the root hairs help, because they protrude out beyond this narrow band around the epidermis, and they form their own depletion zone. Effectively, they're exploiting new soil. But even so, in the phosphate-poor upland soils, there's still great difficulty in getting in sufficient phosphate to support the plant's growth. And this is where the endomycorrhizal partners are so useful. This is an endomycorrhizal hyphae, just one of them. You've got to imagine lots of these sticking out of the root. And they protrude way out into the soil, absorbing phosphate very efficiently out here, far beyond the root hairs. And then they deliver the phosphate into the cortex, and we've shown the hyphae actually ending inside the cells here with this little spiral structure. But what about the other ions? Well, some of them, like nitrate and potassium, do enter with the fungus. But more important for these other ions is the fact that with phosphate restriction on root growth removed, the whole root system grows much better. So it exploits far more soil, so it takes up far more of the other ions. And so you might conclude that endomycorrhizal partners would actually facilitate the uptake of cesium in the upland soils. That certainly seemed a logical conclusion to me.
Yes, that's exactly what we expected, but it's not what we found.
Oh.
In laboratory experiments, we found that young mycorrhizal heather plants actually absorbed less cesium than the non-mycorrhizal controls. However, although the mycorrhizal plants had absorbed less cesium overall, they had transported more of it to the shoots, which is the part that the animals, such as the sheep or grouse, grazes. So the presence of a mycorrhizal association may act as a link in the transfer of radiocesium between the soil and the grazing animal.
But I'm puzzled though, Jill. I mean, why does the mycorrhizal association increase the transfer of cesium to the shoot?
We simply don't know, and it has to be said that there is a great deal that we don't understand about the uptake of cesium by plants. Much more basic research is required before we get to the bottom of the problem.
So far, we've been looking at nutrient uptake and then how the ions move from the roots to the shoots. But for Chernobyl cesium, that's not the whole story. Plants around here are still, many of them, radioactive. Even though they've shed leaves and they've died down to ground level every winter, let alone being burnt in heathland fires. Now, if these were lowland plants growing on a reasonably rich soil, all those shed organs, the roots and the shoots, would have contained cesium. It would have been released during decomposition, and then a lot of it washed away, leached from the soil by rain. But it's not like that on these nutrient-poor upland soils. For one thing, these plants hold on to their nutrients very tightly. When they die down or leaves fall off, they withdraw the nutrients before this happens, taking them into the perennial parts, the woody tissues or the roots. And then they remobilize them in the spring, and in that way you get very efficient internal cycling of the nutrients. The cesium or the other nutrients that are left in the plant litter, well, they're released in the surface layers of the soil, and then they're almost immediately reabsorbed by the mat of mycorrhizal roots. So you get very tight external cycling of nutrients too, and there's very little lost by leaching. In these nutrient-poor uplands, this is particularly true for cesium.
Cesium, you'll remember, is an element closely related to potassium, and potassium is in short supply in the upland soils. Work at Merlewood on the roots of a common upland grass, Agrostis capillaris, has shown that when the grass is grown in potassium-deficient soil, the root's capacity to take up cesium is up to 12 times greater than that of roots grown under optimum conditions. Which means that on the potassium-poor upland soils, the grasses on which the sheep graze have a high capacity for taking up radioactive cesium. So the problem facing the Cumbrian farmers is that because of the way this upland ecosystem works, Chernobyl cesium has been concentrated and well and truly locked up in the vegetation. So let's just recap on why those early predictions were so wrong. First of all, the acid peaty soil in upland areas means that cesium is more available to plants than in lowland areas. Secondly, potassium deficiency in upland soils, and hence upland plants, increases the uptake of the cesium. Upland plants also tend to have an efficient system of internal cycling, which means that cesium, once taken in, does not readily leave the plant. And lastly, mycorrhizal fungi cause tight external nutrient cycling, and the Merlewood research has shown that they increase cesium transport to shoots, at least in heather.
If more had been known about the physiology and ecology of upland plants, then we might have been better able to predict the effects of that Chernobyl fallout, and we certainly wouldn't have misled the sheep farmers so badly. A fuller understanding of the ways in which mineral ions are taken up and recycled in different ecosystems is essential if we're to be able to predict the outcome of any future Chernobyl-like incidents. And until we have that understanding, we'd better be very cautious indeed about releasing any potentially toxic ions into the environment.